like the aldol reaction, we can do this inside of the same molecule. So if you want to figure out if this will work, start with one carbonyl and number, and if you find alpha hydrogens 5 or 6 carbons away, then it'll undergo a ring closure. So 1, 2, 3, 4, 5. Right? This is our alpha. This one right here ended up being the leaving group. Down here, let's make sure we can draw this mechanism properly. And this could be given to you. This is a 1, 2, 3, 4, 5, 6, 7 carbon compound. It could be drawn flat like this. I think that's how we did it in one of your activities after class. So 1, 2, 3, 4, 5, 6, 7. Like we said, start with one of the carbonyls and see if there's alpha hydrogens 6 away. In this case, there are. We'll just abbreviate this a little bit by starting with the enolate right there. Right, that's what we would get by deprotonating with ethoxide. But what can happen then? Carbon 6 will attack carbon 1. We'll end up with the 1, 2, 3, 4, 5, 6. So on carbon 1 will be O minus and ETO, right? On carbon 6, attached outside of it is C double bond OOET, right? So what happens, the alkoxide intermediate comes down, kicks off ethoxide, the leaving group, and we end up with the beta keto ester, just like with any other Claisen reaction, except this one has a name to it. Dieckmann, another chemist from Germany, credited with him because this was actually one of the first very practical ways of making 5 and 6 membered ring compounds. Say we have the product right here of a Claisen reaction or a Dieckmann cyclization. Since we have 2 carbonyls beta to each other, and remember the second step, right, of course, is, right, we have, I probably better draw that. The direct product of this after deprotonation is the enolate ion, so that's why we, in a second step, reprotonate to add that H back in. So you could reprotonate and get that neutral product, then you could deprotonate it again and alkylate there. Or if you're doing this all in one container, you could just forego that reprotonating step. This is the direct product of the Claisen reaction. Then if you add something, right, some sort of primary alkyl halide, you can do a regular old SN2 reaction, right, where we'll have, see if I can draw this small up here, CO2ET, we have an enolate, CH2CH, CH2Br, that's allyl bromide. It's a primary bromide. We do an SN2 reaction, and we alkylate right at the alpha position. Then we also learned in the last chapter, if we have a beta keto ester, like we did in the acetoacetic ester synthesis, those malonic ester and so on syntheses, it can decarboxylate. So with H3O plus and heat, that does 2 things. It hydrolyzes the ester to the acid, C double bond H, right, like that. And then we also have our alkylation that happened. And then remember what happens in decarboxylation. We end up with the enol, which retautomerizes to the keto form, and we lose CO2 then. So the ethanol came from hydrolyzing that ester. So sort of another way to think of this is if you have an ester group attached to the alpha carbon of a ketone, that ester group can go away, right? So that's sort of also known as a temporary ester group. So looking way back at what we started with, we can do the cyclization that gives this ester group attached on the alpha position. That makes it easy for us to alkylate alpha, but then that temporary ester group goes away with just acid and heat. Hydronium hydrolyzes the ester. Then, since we have a beta keto acid, we can decarboxylate.